Hi everybody, welcome back to Mathematics 1 Engineering Math. So this week we're going to continue with trigonometry, and in fact what we're going to do is we'll see some formulas that relate trigonometric identities with triangles. In fact, there's a very close relation between triangles and trigonometric formulae, and that's where the name comes from. We'll see couple of formulas in that respect, and then we'll also do some height distance problems. So these are the first time that we actually solve more or less realistic problems that involve trigonometry. For the subsequent weeks, we're going to move on from trigonometry and do some geometry and limits and continuity. And I also want to point out at this point in time that there will be a Q&A session on Monday the 13th. So with that, let's dive right in and move myself over here. What we're going to do is we're going to cover trigonometry first in right-angled triangles. So triangles with a right angle in them. And then we'll move on to general triangles, so triangles that are no longer right-angled. And we'll see that there's also some nice relations between the length of the sides, the angles, the perimeter, the area, and so on. And so then we will cover some perimeter formulas, so formulas that have to do with the length of the sides, and some formulas that have to do with the area of the triangle. And we'll finish it off with the height and distance problems that I mentioned. So first, let's relate trigonometric functions with right-angled triangles. And in order to do that, I'm going to draw a right-angled triangle like this. And I'm going to call this angle right here alpha. And I'm going to try to say something about alpha. So let's also call this point O. Let's call this point P and this point Q. Then a little bit of terminology first. So we're interested in alpha. So if we look at the triangle from the perspective of alpha, we're going to call the length PQ the opposite side. The length OQ, that's the adjacent side. And OP, the remaining one, that's the hypotenuse. And what we're going to do now is relate sine, cosine, and tan of alpha to different proportions of those lengths of the sides. So in order to show you how that works, I'm first going to have to add one more ingredient to the figure. What I'm going to do is I'm going to draw a unit circle on top of the triangle. So let's imagine that this length here, right, the green line, that's 1 in length. And now let's draw a unit circle like this. So we have this arc, and then the unit circle continues around the origin. And I put it in dots because that part of the unit circle is not so important. It's this arc that we're going to look at. So this right here is a unit circle centered on O. And now let me also take that point where the arc intersects the hypotenuse and call that P prime, and then draw a perpendicular. So this line right here is perpendicular to the base, and let's call this point right here, let's call that Q prime. Okay? So now if you stare at that for a little bit, you see two triangles. You see the big triangle OPQ, and you also have a little triangle OP prime Q prime. And there's a very nice thing that we can say about these two triangles, and it's the fact that they're similar. So triangle OPQ and triangle OP prime Q prime are similar. And similar triangles, if you've forgotten the definition, similar triangles means that the angles are the same, but one triangle is a shrunken or an expanded version of the other triangle. So same angles. And these two triangles do have the same angle. They share the angle alpha here. They both have a right angle right here. And therefore also the third angle has to be the same. And now what does that buy us? Well, in similar triangles, the ratios of the sides are equal. So the ratios of the sides are equal. And if we put that in mathematical terms, what we have is that OP prime, the length of that side, divided by OP is equal to OQ prime divided by OQ, and that's equal to P prime Q prime divided by PQ. So that's a very important relation that we'll exploit in a minute. But first, let's look a bit on the side here. Let's look at the small triangle OP prime Q prime. So if I lift that out, this is my angle alpha. These are my points. And now I know one more thing about the little triangle, and it's that the hypotenuse is equal to 1. And why is that? Well, I drew that unit circle, and I said the point P prime is what you get when you intersect the unit circle with the hypotenuse. So I know this length right here is the same as the length on the base right here. That's 1. That's great, because now what I can do is I can give P prime coordinates, cosine alpha, sine alpha, and that tells me directly all the lengths of the sides in the little triangle. So what do I know? Well, I know that OP prime, that was 1. I already know that. OQ prime, that's this length right here. That will be cosine of alpha. And P prime Q prime, that's that length right here, that is sine alpha. So that completely determines my little triangle, and now let's go back to the big triangle, and for that I'm going to use these proportionality formulas. So first, let's start with the last expression here. Let's write it again. Sine alpha is P prime Q prime, and I can rewrite that as P prime Q prime divided by OP prime. Because this thing right here, that was 1 because of the first expression. And now, if you use this formula here, it's not exactly the same. You have to reshuffle the different sides a bit. You'll get that P prime Q prime divided by OP prime. That is equal to PQ divided by OP. So these are the sides of the triangle in the big triangle, and we give them names. So P prime Q, PQ rather, that's the length of the opposite side, and OP, that's the length of the hypotenuse. So actually, let me stay with this formula for just one more second. So this is a very important expression. This tells us something about sine of an angle as a ratio between two sides in the right angle triangle. So it's, now let me use some colors. So sine alpha is opposite divided by hypotenuse. So it's opposite divided by hypotenuse. Okay, so let's move on. For cosine of alpha, we can do the same thing. That's OQ prime, and that's OQ prime divided by OP prime, again because OP prime, that's 1. And then if you look at a formula with a star and you rewrite the fractions just a little bit, what you'll see is that this is equal to OQ divided by OP. Now OQ, that's the adjacent side, and OP, that's still the hypotenuse. And so once again, we get a formula for a trigonometric function as a ratio between different sides in the triangle. So in this case, it's the adjacent divided by the hypotenuse. And last, there's a formula for tan of alpha, and you can derive it just by deriving sine or dividing sine by cosine, and what you'll get is the opposite divided by the adjacent. So the opposite divided by the adjacent. So you see in each case you have to select the right lengths of the sides and divide them in the correct order, and you get sine, cosine, or tan accordingly. These are very important formulas. Copy them on your formula sheet, but I would also recommend memorizing them because they're so fundamental that you're going to be using them all over the place, and it's good to have them at your fingertips. So let's do an example, or a couple of examples. So what I want to do here is I want to find sine of alpha, cosine of alpha, and tan of alpha in the following triangle. So nice right angle triangle like this. This is alpha, this side is 4, and this is 3. And I want to find those 3 functions without first calculating alpha. So what I can do is, well, first of all, I know, and this is my right angle, I know 2 of the sides, but I don't know the third one, so let's calculate that. So for the opposite side, we can use Pythagoras' theorem. And we have, call this x, that 3 squared plus x squared is equal to 4 squared. So if you clean that up a little bit, you'll see that x squared is equal to 7, and therefore x is square root of 7. So that's good because now we can use our trigonometric formulas to calculate the rest. So we know sine of alpha is opposite over hypotenuse. So that's square root of 7, what we just calculated, divided by 4. Cosine of alpha, that's adjacent divided by hypotenuse. So that's 3 by 4. And tan of alpha, that's opposite divided by adjacent. That is square root of 7 divided by 3. So this is just substituting things into the formula and deriving the result that way. So let's do another example. So for this example now, I'm interested in find the length of the sides A and B. And again, there's a triangle to complete the picture. This is A, this is B, this is a right angle. This is 30 degrees, and the other side is 12. So here I have to say something about the opposite side, and I know the hypotenuse, so the sine is going to be a good start. And I know sine 30 is equal to a divided by 12. Sine of 30, that is 1 over 2. And as a result, I find that a is equal to 6. Likewise, for the cosine, I know that that's adjacent, b, divided by the hypotenuse, 12. Cosine of 30 degrees, that's square root of 3 divided by 2. And therefore, I have that b is 6 times square root of 3. If you stop here at your exam, this is perfect, assuming that you did calculations correctly. But I want to show you there's a small check that you can do to confirm that your answer is not wrong. So here you can check with Pythagoras theorem, because you know this is a right angle triangle, so the sum a squared plus b squared has to be equal to 12 squared, the hypotenuse side. So let's calculate that. A squared plus b squared, that's 6 squared plus 6 squared times 3. That's 144, which is 12 squared, and yep, that's the length of the hypotenuse squared. So our check worked. This doesn't guarantee that your answer is correct, but if the check does not work out, then you know you have to go back and double check your calculations. And then last, but definitely not least, we're going to do a text problem together. So these are interesting because you have to do a little bit of reading and extract the math first before you can calculate. So the problem statement is, we have a student who's somewhere in Songdo, maybe they're out having lunch or dinner, and they see the top of the POSCO tower, you know, that very tall tower, and they see it under an angle of 30 degrees. They also know that the tower is about 300 meters tall, and what they want to know is how far away are they from the base of the tower. So the mathematical elements here are, well, there's an angle here of 30 degrees, that's going to be important. We know that the tower is 300 meters tall, and we want to find the base of the tower. So that's what we're interested in. So now we can make a drawing. So I have my tower over here, and this is my ground level, and I'm standing here, or the student is standing here, and they're looking up at the top of the tower like this. And what we know is this angle is 30 degrees, and this side is 300. So let's also call the base of the triangle x. So x is what we're interested in. And now there's a formula that's going to help us, because we know the opposite side, we want to know the adjacent. That should shout the formula for tan at you. And we can use that. Tan 30 degrees is equal to 300 divided by x. I know that tan is equal to 1 over square root of 3. So if I simplify that a little bit, I get that x is equal to 300 times square root of 3. And that itself is about 520. So that gives us our solution. And just to wind down the video a little bit, if you go and look on the map, then the map of Songdo, then maybe if this is the POSCO tower right here, then maybe the student is here in the park on top of the hill having a nice picnic.